Yes, I hope I'm audible to all of you. Let's get started. So, just yes. So I welcome you all. This is AICT sponsor Prerna Center for SST student at Vidya Pratishthan Kamalnayan Bajaj Institute of Engineering and Technology Baramati. Today we will have this session for the subject electrical and electronic measurements, and the topic we will cover is bridges and the measurement methods, and then we'll look simultaneously look for gate questions. Okay, so this is the topic coverage for today's session. Today we are starting with the new topic, the new subject, that is electrical and electronic measurement. Okay, so let me go to the next slide. Okay, gate syllabus 2022. So this is topic wide weightage which is allotted for your particular subject. For your EMI, we are having 4.5. So let's say around 5 marks, which is allotted in your gate exam. And accordingly, we'll proceed for this session. So let me just share my slide. Yes. So what we'll cover for this is a gate syllabus. We'll cover the bridges and the potentiometers. Then we'll start with the measurement of voltage, current, power, energy, then power factor. Then we look for the different instrument, transformer, digital voltmeter, multimeter. Then we look for certain frequency, time, and phase measurement. At the end, we look for the error analysis and oscilloscope. Okay, yeah. So let's get started with. Let me just close this. Okay, yes. So this is. mm, Yeah, yeah. Okay, okay. Yes. So as you're well aware about the electrical instrument, that what we use so far for the measurement of electrical parameter, whether it is voltage, current, phase measurement, watt meter, energy meter. So all those quantity that we are supposed to measure, that will look for this session. So basically, this is the electrical measurement where we look for. So we are using this electrical measuring instrument for various electrical aspects. Like this instrument we can use for the measurement of current, voltage, then your power, frequency, fluxes. So there are different types of measurement that we have come across so far, that is ammeter, voltmeter. So for the current measurement we have the ammeter, which measures the current. For the capacitance, measurement of capacitance of the component, we will have capacitance meter to measure the current. Okay, let me know what will the which device we will use for measurement of current without physical connection. Okay, what I'm asking, if you want to measure the current without physical connection, which device you will use? Which device you will use? Okay, for the physical connection we have ammeter, we have multimeter also for small application. For if I want to measure the current without physical connection, so which type of device or equipment will be used for the electrical measurement? Any guess? Any guess about current clamp meter? Clamp. Have you come across the clamp meter? The clamp meter is the okay. Let me show you, so you will get better visualization of it. Yes. So this is the device where we pass this conductor through overall this section, and we are just clipping over the sides. So we'll it acts as a measuring devices for our electrical current measurement. So this kind of device we will use as a electrical current measuring device without any physical connection. Now question is where it will be utilized. Okay, because whatever the instrument that we are looking for, all the instrument are somewhat extent are utilized in our daily application. Likewise, if you are considering the battery session, so every battery when we are putting on the charge, we check for its gravity, we check for its current parameter, and before charging and after charging. Correct. Another scenario when we are looking for any devices or any vehicle who are operating on the batteries, at that time also we will look for the use of this clamp meter. Most of the cases when we are working on three phase application, where we having handling 440 volt as a power rating. In that case, don't you think the multimeter that we are using for the small scale application, it get more chances of getting short circuit? So to avoid that, we need certain instrument who will measures the live current without any physical connection. So for that we have the clamp meter. Correct. So this is current which is called as clamp meter, or which is utilized to measure the current without any physical connection. Correct. Apart from that apart from that, if you want to measure electricity, so for the electricity measurement we have the energy meter. For the frequency we have the frequency counter. Then you might have come across LCR meter. Correct. So LCR meter will measure the inductance, capacitance, resistance of a component. Correct. Then we have a general purpose instrument which measures your voltage, current, resistance, and some types of other quantities as well. Okay, which type of instrument it is? Now this is, you are well aware, that is multimeter. Correct. It's a multimeter. So multimeter is one instrument where we have utilizes from the DC as well as AC, but for three-phase application, multimeter has certain type of limitations. Okay, then if there is a we want to measure the uh, network parameter, so we have network analyzer. Correct. To measure the resistance of component, we have ohm meter. To display the waveform, single signal, or any type of frequency timing measurement, so we will use which kind of devices? Yes, you can drop in chat box, no doubt. We use oscilloscope. Correct. So such type okay, one more is for drives, for motors we are using to measure the speed of the application. We are measuring, we are what we are instrument we are using the tachometer. Correct. So say there are plenty devices that can be utilized for the measurement of electrical instrument. These are electrical instrument. Okay, now let us see all these is electrical instrument one by one. Okay, as per the getter perspective. Okay. Yes. See, the first we will start with the typical tree diagram, which consists of all the absolute secondary instrument. So what do you mean by absolute? What do you mean by secondary? We'll go to the detail. Correct. See, so this is the tree diagram which shows this is absolute electrical instrument will be categorized as absolute one and the secondary instrument. Absolute one means what? This kind of instrument which does not show direct reading, which does not show direct reading. Okay, here it is. Absolute instrument. This instrument does not give the direct reading but gives the in terms of instrumental constant. Okay, so most of the time I think you have come across the constant, correct? Likewise, absolute electrometer and a tangent galvanometer, there are certain constant. Okay, so these instruments are used for the research laboratory. Okay, absolute instrument. But we people are involving in secondary instrument. Secondary instrument is gives the direct reading. Okay, so direct reading in terms of indicating, in terms of recording, in terms of integrating. Okay, in terms of indicating, recording, and in terms of integrating instrument, correct? So the secondary instrument give, in short, it is showing direct reading. That is the main use of this secondary instrument category. If you want to categorize the electrical instrument, first is absolute one, second is the secondary instrument. Okay, so what is the basic difference? These are the shows the reading directly. Here it shows in terms of certain instrumental constant. So you might have come across K constant, galvanometer G constant, tangent constant. So they represent in terms of certain constant and which have certain values. Okay, that is absolute instrument. Second instrument which shows the direct reading at that particular instant. Okay, then it is called an indicating instrument. If they are recording something, so it is called as a recording instrument. Okay, so we will go in detail of all this instrument one by one, correct? Yes. So let us start with the first one. What do you mean by indicating instrument? Yes, any guess? What do you mean by indicating instrument? These are the example: electromechanical and electronic. Yes. Yes, any guess? Yes. So such type of instrument, as I said, secondary instrument are belong to the which category? Direct reading. So such type of instrument, which is called as indicating instrument, which shows a instantaneous value. Okay, that for what we are measure user utilizing it. Okay, so basically it consists of pointer if you are using for the digital analog one, and it shows in terms of display if you are this indicating instrument in digital form. Okay, so what is indicating instrument? This instrument will give the instantaneous value. It will produce the instantaneous value of the quantity to be measured for in terms of scalar and pointer mechanism. Now this is analog one. If you are using a scalar or pointer mechanism, that is nothing but analog one. And for the digital one, it's showing in terms of a display. So the best example are here: PMCC, moving iron instrument, dynamo wattmeter, frequency meter, power factor meter. So all are the part of the electromechanical and electronic instrument. Correct. Now the next one is recording instrument. So what is the basic difference between indicating and recording? Yes, let me know. Those are present. Indicating instrument, recording instrument. Basic difference. It is in front on the screen itself. Just let me know.
Indicating instrument just indicate the value and recording instrument records that.
Yes. So I'll give. Suppose you are having multimeter. So it is which type of indicating or recording?
Indicating
Ammeter.
recording.
Ammeter is recording. Voltmeter.
Also recording.
So how you can say ammeter is recording?
So, difference analog and digital difference.
Okay. And the energy meter.
Uh, it records the energy which is utilized.
Yeah. It is whatever the energy consumption you have made for a
Yes.
particular duration, it gets. So it belongs to the integrating. Correct? Yes. So the recording instrument is what? Which records the value. This is a basic thing. So the types of recording are recording voltmeter, wattmeter, your oscilloscope is one of them. And the third one, that is only one belong, that is integrating instrument. So integrating instrument which adds the measured value. Okay, so at the end you will get the total consumption. It doesn't show you the consumption of particular day. It get integrated individual value at each day, and at the end they'll add up or sum of all the measure value, that is nothing but indicating instrument. Integrating instrument. Okay, so best example is your total electricity bill. Okay, this is the best example because in integrating instrument we are having only this energy meter. We have one instrument that is energy meter. Okay, sometimes we'll measure this in kilowatt hour, ampere hour meter. Okay, these are the integrating, and the one more that is indicating instrument. Which one is remaining is indicating instrument. So we have the, okay, they are not shown. Okay, so we'll start with the one by one. Clear? Apart from that, now we'll start with the indicating instrument. So what we have done, we have seen the basic prerequisite for the electrical instrument: absolute one, secondary instrument, then indicating. So these are the basic category, then for the recording, and then for the integrating. Okay, yes. Now we'll start with the basic torque. Okay, so before proceeding to that one, let us understood different equipment or different devices which are categorized on the basis of indicating instrument. Okay, just have a look or you can take a screenshot of it. Okay, so what type of instrument we have? We have PMMC, which work on the magnetic effect. We have ammeter, voltmeter, wattmeter, which works on the heating effect. See, these are the added point as per the grid perspective. Your ammeter, voltmeter, and wattmeter, which works on the heating effect. Then you have Hall effect. Then you have energy meter, which works on the electromagnetic effect, and we have electrostatic effect, that is voltmeter. Okay, so let us start with all this. So before start with the indicating instrument, let us understood the range, because any of the instrument when it calls in the market, or we can say they utilize for a particular application. Suppose I'm using voltmeter. Okay, but there are plenty ways or plenty range of voltmeter that we can utilize. Suppose I'm using for DC, so DC range will be the difference. I'm using for AC, so a single phase it will be different. For three phase, again it will be the different. So this range parameter get vary. So the range section will decide the meter is calibrated to read a value for minimum to maximum. So this is a range. Range means what? Minimum to maximum. We cannot use it for the beyond its application. So same example as our as at the start we have discussed. Yes. What was that? Which example we are look for?
Instruments,
Which one?
ammeter, voltmeter.
Yeah. So basic one is a clamp meter. Correct? Because clamp meter is used for the basic application of three phase one, where we pass that conductor throughout that clamp and we measuring the current without any physical connection. Correct? But in multimeter we have to connect it physically, and it is very limited for the particular voltage range. So these are the range. If we are using same instrument for another part of application, or application may be same or may be different, doesn't matter, the rating or the energy rating, electricity parameter rating, it may differ. Suppose I'm using it for another value of range, so definitely it will affect my instrument. It get damaged, it get misbehave, it will not show accurate reading. So that's why we need a calibrated result. Okay, so that's why here also they have said a calibrated to read a value for minimum to maximum. Because some of the time, do you know the tolerance? So tolerance means what? Somewhat of plus or minus can be acceptable. This is what tolerance say. Some kind of plus minus can be acceptable, but beyond that, your measuring instrument is not ready to use for the particular application. Correct? Yes. Now let us look for the main important part, which is common in our electrical measuring instrument, that is torque. So the basic function of, okay, so we'll start with this actually, then we'll look for the next thing. See, when you come across any indicating instrument, any indicating, which type of this one, any we are, what we are looking for, indicating instrument. When you are look, okay, span is also there. Span is nothing but a length of a scale. It can be calculated by algebraic difference of maximum and minimum value. That is nothing but span. For which span it is, it can be allowed for your instrument. Yes. Now, when we operating for on the base of the indicating instrument, so there are basic torques are required. So which torques? Deflating torque may be there, controlling torque may be there, damping torque may be there. May be there. So these three torques are mostly responsible for our indicating instrument. Correct. If one of them is one, each of them have basic approach or basic functionality. If one of them is missing, so your indicating instrument will not work properly. Yes. So let us understood by the deflecting torque. Correct. So this is one of the important requirement. We can say it is one of the requirement in our indicating instrument for for as its name shows, it's a deflecting torque. Okay, so it is a, when the, we can say, when the instrument is connected in the circuit for the given measurement in our electrical quantity, so whatever the deflection that we achieve through the pointer, that is nothing but your deflect, which caused by the deflecting torque. Okay. Yeah. So what is the important aspect from the gate perspective? So this torque, we can say it is electromagnetic torque which produce deflecting torque to the pointer. Okay. So whatever the amount of deflection this torque will produce, accordingly the pointer will move from zero position. Okay. So the you have might have one question that how the deflection of the pointer, how we can say it is, or how much amount it will, how much degree it will get display. So it depends on your, totally depends on your deflecting torque. Okay. As this deflecting torque causes the moving of pointer from zero position to the desired deflecting measurement, so that we are considering the actual measurement. Correct. Okay. Now, so as they are saying, this is electromagnetic effect or electromagnetic torque. So definitely, when you are saying the electromagnet, so there will be a moving coil instrument and dynamometer type instrument. If you are saying it is electromagnetic effect, so definitely there will be induction type instrument. Okay. So whenever there such type of instruments are used, there will be the presence of electromagnetic torque. Correct. Yes. So, okay, I think you are aware about the different types of instrument that is works on the electromagnetic effect. So that is nothing but your induction one. Okay, so induction one instrument, that involve ammeter, voltmeter, wattmeter, energy meter. Okay, so this type of instrument which works on the AC supply are the electromagnetic induction effect. Correct, which produces most of the indicating instrument as a deflecting torque. Correct. Yeah. So here they have shown this is only deflecting torque. The pointer indicates full value. Okay. Yeah. Next torque is also there, that is known as controlling torque. Now deflection has done. Now this, see, this deflection has done. This is my 0 point. This is my last point. So what we say in technical word, we'll say it is a null position or zero position. This is last position or full scale deflection, FSD, which is called as full scale deflection. Correct. So this controlling torque, with the help of this deflecting torque, the pointer will get deflect from the null position. Always your keep in mind, at the initial your pointer will be always at the null position. Okay, it is not rest at this. Okay, sometimes such instrument you might have observed while performing the experiment, that some pointer are stuck at this position. Means if they are not operating in operating condition, still the pointer is not present at the null condition, it is present somewhere. but it is not totally at the zero position. So such type of instrument are, what you understand from this such type of instrument, they are, yes, do you get my questions, what I ask?
No, sir.
Shall I repeat the question?
Yes, sir.
Hello,
Yes, sir.
shall I repeat the question? Yeah.
Yes, sir.
So
Yes.
question is, I'm asking practical one. Huh? I'm asking practical question. See, okay, consider only this screen. What they are saying, the pointer is at null position. Is it?
Yes, sir.
Pointer is at null position. How? What I say? Null position is what?
Zero.
Yeah. So is the pointer at null position?
No, sir.
Yeah. So it is midway or nearby the null position. Okay. So have while perform, yeah, while performing any experiment, if you observe such type of instrument, and this is a practical scenario. I'm not talking about the theoretical. This is a practical scenario. While performing any particular application, forget about application. In the real time scenario, if I'm using the particular instrument for my particular measurement, and I observe the analog instrument is having certain kind of deflection without any live condition, so these instrument are good to use or not?
No, sir. It
No.
becomes a
Why?
error in that.
Yeah, so whatever the amount of deflection, it will get add in my measurement. In same case, in real time scenario might come across the weighing machine. When you go on the weighing machine and you can observe, the reading is not totally 000. It's showing that 1 point something, or 100 150. It means that is the error that is introduced in the my measuring instrument. Okay, and so that's why we are having error handling technique, correct, where we remove the error. And after removing the error, how we will check whether the error has been removed or not? With the help of with the help of calibration, correct. So these
Yes, sir.
all are interlinked. Okay, these all are interlinked. Okay, yeah. So let us move to the next one, that is nothing but controlling torque. Yes. So what controlling torque is, the purpose functionality of this controlling torque will be what? See, now what we have done with the help of deflecting torque. See, first we learn all this torque scenario, because each and every indicating instrument we are utilizing this one. Okay, so that's why we'll go in deep of it, and then after we'll look for the next functionality. So in controlling torque, what they are saying, controlling torque is nothing but, as word is said, we have to control the torque what is produced by the deflection one, correct. So we are controlling the opposite, or we are saying opposes the deflecting torque, correct. And this torque get increased with the deflection. Okay, that if there is a deflection is large, so that much amount of controlling torque we will require, correct. Suppose the basic practical example, we are on the slope and we are riding to a vehicle bike, and is it necessary to apply the brake?
No, sir.
No. But for the ropeway or for the particular highlight thing or lift way, suppose we are moving from the lower floor to the upper floor, so definitely whatever the amount of weight, the gravitational weight, accordingly opposite torque need to produce to where lift should move from lower to the upper floor, correct. It means that every this works on the physical science, that every action there is equal and opposite reaction. Suppose my deflecting torque is producing certain deflection for the pointer, definitely I need equal and opposite reaction from the, again, torque I require. So that is nothing but your controlling torque. Okay, so because of what the importance of this controlling torque, what will the importance? Yes, any guess? Why there is need of, as we with the help of deflecting torque we have moved the pointer, so why there is need of controlling torque?
Pointer moving.
Yes, point of,
pointer
Yes, you're right. You're right.
to control the deflection of pointer from one position to another.
Yeah, to control the deflection of the pointer. Correct? Yes. So when we want to control anything, we have to apply equal and opposite force. Correct? So the deflection of the pointer is highest. So controlling torque will be low or high. Controlling torque will be low or high if the deflection of pointer is high. Okay, I'll give condition if the deflection of pointer is full scale deflection. Now you know the basic difference between full scale deflection. What do you mean by full scale deflection? Okay,
Sorry, sir.
you don't know about full scale deflection? Okay.
No,
What
sir.
is zero position? If
Pointer is
point is
null
at null
position.
position. And what if the pointer is at final position? Yeah.
Full
So
scale
that is
deflection.
full scale deflection. Purpose of your pointer is what? To show the deflection, to show the measurement. But with the deflection, we'll come to know. See, to understand the basic calibrated scale is also most a beautiful skill. Therefore, this is at null position. This is called null position. If my pointer is start at from the null and without stopping here, it directly goes to the final one. That is known as full scale deflection. Correct? Full scale deflection. Suppose you are having particular weighing machine. It's a capacity of 100 kg, and some one person who is standing over there and he is having weight of 107 kg. So the weighing machine will show, weighing machine will show full scale or null deflection.
Full
Yeah,
scale.
it means that whatever the load that we applied on that instrument, it is it is it is out of range. Okay, that's why it is showing full scale, because after this full scale we cannot proceed further. So that's why it is showing full scale deflation. So don't you think such type of loading is okay with the below rating instrument? Obviously not, because we cannot get correct reading. Okay, if it is weighing, we say, take the example of weighing machine. Now it is showing 100 kg, but what is exact weight? It is 107. Okay, so we don't get exact reading. So that's why they are saying you have to use appropriate range instrument for the particular application. Correct? Yes. So what do you mean by controller torque? It is equal and opposite torque for the develop deflecting torque. Correct? So that's why we always say TD is equal to TC. So what do you mean by TD? Let me check whether it is given over here or not. Okay, they are not given here. So that is nothing but we say TD is equal to TC. So TD is nothing but your deflecting torque. It should be equal to TC. Correct? It means that TD and TC, if they are equal and opposite, then your pointer will come to the rest. Okay, but controlling torque increases with the deflection of moving system. If the deflection is large, your controlling torque will be large. If deflection is low, your controlling torque will be low. Correct? So the final position of pointer will be achieved as per the deflection. Correct? So as per the electrical quantity. So here electrical quantity, now we are generally we are using generalized term, that is electrical quantity. But in electrical quantity it might be anyone, current, voltage or power, anything. The functionality of this pointer, deflection torque, controlling torque, and one more that we look further is remains, always remains same. Correct? Yes. So what are the main features? Controlling torque. Controlling torque will bring the pointer to zero position. Okay, when the deflecting torque is removed. Means what? Now we look for the first purpose. First purpose is what? Whatever the deflection torque, the to control torque will produce equal and opposite one. Okay, that's fine. But now we have taken the reading. We have consumed the reading. We got the indicate what we instrument we are using, indicating instrument. We note down the reading. After that, we have to bring this pointer to the null position. Okay, do this action will take place through the deflecting torque to make your pointer at null position. Just think over it and tell me.
I don't understand the question, sir. Your voice is breaking.
Okay, just 1 second. I'll now.
Yes, sir.
Yeah. So question is, with the deflecting torque, what we have done, we have moved the pointer from the null position to the required scale. Correct. And what we are saying, controlling torque, with the help of controlling torque, we are producing equal and opposite torque to oppose the deflecting torque. Okay, that first functionality that we have succeeded. Now this point is at certain position. Now look into this scenario. Point is at certain position. For next reading, we have to bring this pointer at the null position. Is it?
By removing the deflecting torque.
By using?
By removing the deflecting torque.
No,
It
but
can be at null position.
deflecting torque we have not produced. That instrument have produced that deflecting torque with the help of electromagnetic effect. Correct. When you pass any
Yes.
electrical quantity for current measurement, voltage measurement, power measurement, that are get introduced when you pass a particular supply through that one. According to the which definitely it will related to the quantity that we are measuring. But after that, what? Don't you think there should be one mechanism for this?
Yes, sir.
Yes, yes. Now tell me, what is the operation of spring? A general scenario. Spring. Elongation or contraction, is it?
Yes, sir.
Yes. So what amount of force we are applied for the elongation and we just release it. So it get contract. Is it?
Yes.
Yeah. So what is controlling the first functionality to oppose the deflecting torque and the second one to bring the pointer to the null position or zero position when your deflecting torque is removed. Correct. Deflecting torque is functionality to make the deflection from null position to the final, but when it get removed, the pointer will not get automatically to the null position. Okay, they have to come back. So for that, controlling torque has another functionality to make your pointer to bring your pointer back to the zero when the deflecting torque is removed. Okay, have you understood?
Yes, sir.
Yeah. Okay, but what will happen if this such condition arises when the deflecting pointer not return to the zero position on removing the deflecting torque? If there is certain condition, your pointer is not getting back to the null position when still though we have removed the deflecting torque. So in that case, yes. So as I said, we need to provide certain mechanism. So think the example of spring. Okay. So we have two methods to control this. That is, one is spring control method and another one is your gravity control method. Correct. Spring control method and gravity control method. Correct. So this is spring control method. We can say most of the common method which provides the controlling torque in electrical instrument, and where we utilize a spiral spring mechanism along with its balance weight. Okay, these are the mechanism structures. So suppose this is my mechanism. So at this end, I'll just write, at this end we are having the spring control mechanism. So whatever the amount of deflection, at the time of deflection spring get elongated, and at the time when the deflecting torque is removed, obviously it will get come back to the null position. Correct. That is nothing but spring control mechanism. Correct. So in this spring control mechanism, or we can say spiral mechanism, we have attached this spring to this moving pointer. Okay, let me just check whether the same diagram is here or not for the, so that yes, see what is this w1? It's a counterweight, correct? It's a counterweight. To balance, we can say it's a balance weight. Okay, so at this pointer, suppose this is my pointer, at this pointer we have attached one control spring. Okay, so as soon as the amount of spring deflection that we got, according to that we will we will come back to the null position. Okay, yes. Now next one is gravity control. In gravity control is what? Gravity control is what? The likewise I just show you the weight. Okay, in spring control we have placed spring at this position, and in gravity control at the opposite point of the pointer we have keep some kind of weight. Okay, so we have attached some weight on the moving system which will provide necessary controlling torque to bring the pointer into the zero position. Okay, so these are the two basic ways for moving your pointer at the null position after removing. Please listen it carefully. This works after removing deflecting torque. Okay, till the deflecting torque is present, which torque is present? Controlling torque is present. Okay, and with the help of this gravity control and spring control, we move when deflecting torque is get moved, we bring the pointer to the rest position, null position, not rest, null position. Okay, try to use technical word. This is null, this is FSD, full scale deflection, this is midway of your calibrated scale. Okay, what we call it this scale as? What kind of scale it is? Okay, just yes. Now I'll ask some, I will just highlight, you just let me know what the thing is. This is,
Pointer.
this is,
Scale.
just look into the highlighted
Null
section.
position. Null
Null
position.
position. This is
Full scale.
full scale. And overall, just one second. Overall,
Full scale deflection.
no, no, no. See, I'll repeat again. This one,
Null position.
this one,
Full scale.
and this one.
Sorry, sir. I'm not.
Calibrated scale.
So, okay.
Okay, because we
Okay,
have
sir.
certain reading over here na, 1, 5, 10, 20. 20 is my full scale deflection, 0 is my null deflection. This is my calibrated scale. Okay, now this one, spring control mechanism, and opposite to that, if I place just here, so that is gravity control mechanism. Okay, this is what I'm showing the real-time scenario pic. Okay, and that is much more important for while working on the actual scenario. Okay, now let me just make it zoom out. Yes, then okay, let us just summarize what they have shown us. It is to stop the pointer, okay, for the required final value, means produce the opposite torque. Yes, here they have shown exact equal in opposite direction to the deflecting torque. Yes, but they have not given the next part, that what if the deflection torque get removed, how to bring it back, that what we have added here now. Now the last one is nothing but damping torque. So damping torque is one, as we say we have deflect the pointer, as we say we have control that pointer, correct? Correct, yes. So damping torque is one, but to damp the oscillation of the pointer. Okay, so in short I'll say it is to make, yes, the pointer makes the oscillation with respect to final value. To eliminate this oscillation, damping torque is used. Damping torque means what? Now, don't you think if we are having certain deflection, Pointer, we are talking about the analog one, whatever the current we are looking for, these all are analog one. Okay, so if deflect, because of this deflecting torque and the controlling torque, don't you think this pointer will slightly oscillate at the final position? Suppose this is my final position at 12. At this position, pointer will slightly move back and fro, back and fro. So being accuracy, what always we say in our characteristics, accuracy of indicating instrument should be more. Okay, so to avoid this oscillation of pointer, who will oscillate, pointer is oscillate about its final position, about its instantaneous position, not final, instantaneous position. So to damp that oscillation, we are using damping torque. Correct. So what is the damping torque? Damping torque will produce by a damping or stopping force which acts on the moving system when it is oscillating for the particular instant, or when it is oscillating on the particular position. So that's why we are using damping torque. So damping torque doesn't provide any that much clarity, but yes, is this damping torque will categorize your instrument under 4 1, that is over damp, critically damp, and under damped. Okay, so this damping torque we can say means what, like okay, let us see this scenario one by one. If I'm saying my instrument is under damped, it means what? Under damped means your pointer will oscillate about the final position. If I say over damped, means pointer will be slow if it is over damped. So such type of arrangement they have given. But now the question is how to avoid this. Okay, so we, what we have seen, yes, we can eliminate this damping oscillation by using damping torque. But likewise in controlling torque, we have certain mechanism, that is spring control and gravity control. In damping torque also we are okay. Okay, recording is still on. ठीक है. Just one second, I just need to connect my. Just one second, just. Okay, now am I audible?
Yes, sir.
Okay, okay. Yes. So what we are up to, I think, damping torque. Yes. To avoid this damping torque, what we have, likewise in deflecting torque, controlling torque, we have air. Sorry, we have spring control mechanism and gravity control mechanism. So in damping torque we have air friction, fluid friction, and eddy current friction. Okay, air friction means what? With the help of air, with the help of air chamber. So in this mechanism we are having air chamber. With the help of this, we are controlling the oscillation of the pointer. Another way, we are a fluid friction. So in this fluid friction, we are having certain vanes attached to the spindle of moving, which keep your pointer as null position, or which brings your pointer to the null position or null deflection. And the third one we are having eddy current damping. Okay, so the purpose is what? Purpose is to just make your pointer deflection free or oscillation free. Correct? Yeah. So that is nothing but damping torque. See. So what is the kind note for the gate point of view? Your controlling torque is depend on TD. Okay, as we are saying, your controlling torque is force is equal and opposite to the damping torque, but your damping torque is independent of controlling and deflecting. Okay, okay, I slightly differ. Your deflecting TD is nothing but deflecting, TC is nothing but you are controlling, and this TD is nothing but you are damping. Okay, means what? Your deflecting torque is totally independent of TC and TD, that is controlling and damping. Last one. Okay, so the who is higher? Higher is at deflecting torque, and these two are just a mechanism which is provided for a particular application, particular purpose. Clear? So now we have just discussed what is the role of TC and what is the role of TD. Correct? Yes. Yeah, this is one more scenario. The deflecting torque can be produced by. So likewise, a deflecting torque, we have just see a deflecting torque. So this can be produced in the other way, that is magnetic effect, electrostatic effect, induction effect, thermal effect, chemical effect, and Hall effect. Okay, so because of this effect, with the help of this effect, what you will get? What you will get? You will get a instrument. How? Let us let you know. Just one second. So on the base of this, on magnetic effect, we will have PMMC. We on induction effect, we have certain instrument. For the thermal, we have thermocouple and all. Chemical, for voltmeter, we have electrostatic effect. So on the base of the effect of deflecting torque, we are producing deflecting torque on the basis of this effect. Okay, so accordingly, we will utilize all this effect and we'll look for. Okay, first before that, first we'll look for this. Yes, here we got the diagram for spring control and gravity control. Okay, so this is what a part of which torque? Controlling. As just we have just discussed about the controlling torque. First we'll cover this one because it is related to what we have discussed so far. See, spring control mechanism is the one and the gravity control mechanism one. It is a part of controlling torque which are just to produce equal and opposite uh, torque, and after that when the deflecting torque get reduced or removed, at that time we need to bring our pointer at null position. At that time we need this. Correct? Yes. So what these basic features of this? Okay, just look into the diagram. So you'll come to know. See what they are saying. This is my spring, the circular one. Okay, and this is gravity control. What we have discussed, we have talked about the weight. This is counterweight. Why counterweight? Because we are balancing this weight of this overall deflection by the this weight. So that is called as pointer weight. Okay, clear? Yes. Now this, yes. So this what just we have seen. The spring will be attached to the pointer to control the deflection and to make it at the null position. In same way, the counterweight is there, which is attached at the opposite direction of the pointer, which will be used to control the motion of the pointer and bring back to the null position. Correct? Yeah. So springs, this is nothing but this one. These are connected in series with the moving coil, and this is used by in which instrument? MI instrument. Okay. So where we cannot observe any physical contact between the coil and the spring. Correct. But the on the other hand, we have the counterweight. Okay, so this is only used for a vertical direction only. Okay, this is the basic difference. And the last one, yes, this is about the material, that is spring will made up of the phosphorus bronze. And here we'll observe in the terms of deflection, the weight we are using. Okay, so in PMMC we are having spring mechanism. In PMMC we are mostly having spring mechanism, correct? Yes. Now let us start with the on the basis of. Okay, first we'll look for like one example was there. Yes, yes. On the basis of it, we look for the one example. This is a ask and get exam. A weight of 3.5 gram is used in controlling weight. So that is talking about gravity control. Correct. They are talking about the gravity control. In gravity control instrument, yes, in gravity control instrument, find its distance from the spindle. This distance from the spindle, if the deflecting torque to the deflection of 58-degree is, okay, they have given the deflection also and then given the torque also. Okay, they are given the deflections also and they are given the deflecting torque also, but they are only finding they are asking to find out distance of the spindle. Okay, as what we have say, in gravity control we are attach this counterweight at the end of the opposite end of the pointer. Okay, so for the deflecting torque, to find the weight we have the equation is deflecting torque is equal to mg into sine theta into d. So d is nothing but distance of the weight from the spindle, distance of the weight from the spindle. Okay, so what you have, your equation is td is equal to mg sine theta into d. Okay, so td they have already given. What is value of td? 2.51 into 10 raised to minus 3 newton meter. Then what we required? What we required? Mass. So mass they are already given in 3.5 kg, in gram they are given in gram, we will convert in the kg. Gravity we know that is 9.81, and sine theta, so deflection they are already given. Okay, so just put the values and let me know what is the value. Yes, put the values and let me know the values of distance in mm. We have the formula tg equal to, I'll just highlight it for you, the question. Yes, so this is the question. What the questions? Question is what they have given. They ask for, they are given the weight, they are given the degree of deflection, they are given the deflecting torque also. Only they are asking for the distance from spindle of your weight, correct? And for that we are having the formula Td is equal to mg is equal to sine theta into d. That is the distance. That what we need to find out. Okay, so put the values and tell me the answer. Okay, so what we'll do, we'll simply put the value of td. Td is what they are given, 2.5 into 10 raised to minus 3 newton meter. Okay, first we'll rewrite the equation for the distance. So distance is TD upon mg sine theta. TD they have given, that is deflecting torque is 2.5, 2.5 into 10 raised to minus 3 meter. So we have taken a meter. Here it is 3.5 into 10 raised to minus 3 and 9.1, and then we'll look for the value of sine 58 degree. Okay, so if you simply put the values in all these among equations, so you will get the values as 86.2 mm. This is in mm because we are finding the value for the distance one. Correct? Yes. Okay. So before proceeding further, okay, I'll just 1 second. Okay. So kindly fill this feedback form and we will this resume the session very shortly. Yes. Okay, I'm audible. Okay. Okay, so we'll focus on next part, that is, yes, the effect. As we have started, deflecting torque can be produced by certain effect. So one of them is magnetic effect. So magnetic effect means what? Which works on the principle of Lorentz law. So what the Lorentz law says? As as we are having, whenever current carrying conductor, whenever current carrying conductor placed in a magnetic field, it experiences a force. That force is given by F is equal to BL sin theta. And this direction of the force is a well-known rule, that is Fleming's left hand rule. Correct? The equation, sorry, the force direction is given by Fleming's left hand rule. Okay, so here conductor is moving from right to left. Here conductor is moving from left to right. So by Fleming's left hand rule, we will calculate that one. Okay, now now the next one is electrostatic effect. So electrostatic is with what? When the high voltage is applied, this is a lightning heavy voltage. Now you know the about the lightning surges, which consist of huge amount of energy. Such type of high voltage is applied to the capacitor. Then capacitor plates are charged with opposite polarity. The polarities are here nothing but your positive and negative one, where where we get, if one plate is fixed one, suppose we say fixed one is the charge polarity of negative one plate is a fixed one, and another plate is nothing but your moving plate. Another plate is nothing but your moving plate. So with the help of these, we can say when a high voltage is applied to the capacitor, capacitor plates are get charged with opposite polarities with the help of electrostatic force. Okay, so which force we are using here? Electrostatic force. So what we are looking for, the deflecting torque can be produced by the help of magnetic one, electrostatic, induction effect, then thermal effect, chemical effect. So this is one of them. Correct? Yes. Now, now we'll see next one. Just one second. Yes. So what we have said, in electrostatic, if the one plate is fixed and pointer is connected to that movable plate, then we can see the voltage measured by the pointer, and these are especially used for the measurement of high DC voltage. We can say very high DC voltage can be measured through electrostatic effect. Correct? Then we have come across one more thing, that is damping, and this damping terminology is one of them, that is eddy current damping. Correct? In this eddy current damping, let us see what happened. In this eddy current damping, we are using aluminum vane and permanent magnets for this eddy current damping. And this is most effective damping methods. This because of this method, we are having strong magnetic field because that is a permanent magnetic field. So best example of this is nothing but permanent magnet moving coil, that is nothing but your PMMC. Correct? Eddy current damping by the metal former. Apart from these eddy current damping, one more that what we have, that is nothing but air friction damping. Okay, so as we discuss in this, we are having aluminum vane and the permanent magnet. In same case in air friction damping, the gap between aluminum piston, so this is my piston, and the cylindrical hole must be very small and should be uniform. Okay, so you can just observe here this section is called as air chamber. Okay, so this method is best suited for the instrument which or who are having weak magnetic field. Okay, who are having a very weak magnetic field. So such instruments are moving iron instrument, electrodynamometer, and the wattmeter. Okay, so the wattmeter that what we have used for the measurement that are using based on the air friction damping. Correct. Next one we are having fluid friction damping. Okay, so fluid friction damping is nothing but what? Here instead of air friction or the eddy current, we have used fluid. Okay, viscous fluid we have used. That is nothing but this one. Let me show you. Yeah, suppose this is instrument spindle. Okay, now this is my rotating part, and for this is my disc. I'm using damping oil. So this is nothing but what? A high viscous fluid. We can say it's a mineral oil which is used for instrument having low deflecting torque. So means what? The air friction damping, eddy current damping, fluid friction damping. These are producing one mode is common, that is friction. Friction, because of the friction, their velocity of or with the acceleration will go slow, and in that way we can damp the oscillation of our pointer. That is the main thing. Next, there will be the question, then which one is more suitable and which one is less? Okay, so the effectiveness order, that is called as effectiveness order, which damping is more suitable and which one is less. So for this effectiveness, if you just summarize, that is eddy current is much more on the top, eddy current is on the top, then fluid friction, and then air friction. Okay, so most of the cases that we have come across so far, that is wattmeter, dynamometer, electrometer, mi instrument, so all these are air friction one. Correct. So we are working on this air friction damping. Correct. Yes. Now these are the part of, we have succeeded with the first part, that is nothing but basic electrical instrument. That what we have cover of indicating, recording, and integrating instrument. Okay, then we have seen the basic part of torque, all different types of torque and its classification. Now we will go in detail of each instrument. Okay, so first we will start with the electromechanical and indicating instrument. Electromechanical indicating instrument, these are the same, electromechanical and indicating instrument. Correct. Yes. Now, as we know, these analog ammeter, analog voltmeter, analog ohm meter, all these are what? All the works on the basic principle of certain type of arrangement. Okay, and today we'll look for this arrangement and then we'll solve some numerical based on that. Correct? Also, in this, we'll look for the range extension. Okay, so that is most important and frequently asked in GATE exam, range extension. Okay, so let's get started for this. What they are saying, analog meter, analog ammeter, analog voltmeter, or ohm meter, these are the types of instrument used for the measurements of current and voltage. These are the types of instrument which are used for the measurement of current and voltage. PMMC is one of them, that is permanent magnet moving coil. Moving iron instrument, which is AC and DC. Electrodynamometer type, AC and DC. Electrothermic instrument, that is thermocouple. The electrostatic type instrument, that is AC, which is used for AC as well as DC. Correct. Yes. Now, if we say these are the type of instrument, we will go through the one by one. We will first start with the PMMC. That is always and most frequently asked for the GATE exam. That is PMMC, which is another name is D'Arsenoval instrument, or the abbreviation is Permanent Magnet Moving Coil Instrument. Correct? Yes. Yes. Just quietly look into the picture and tell me where is the your which kind of controlling torque we have used, which kind of control mechanism we have used, and yes, please let me know. Okay. Yes. So the gravity control mechanism that we have used, it is the spring control. Okay. Look here. Have you observed the spring control mechanism? Don't you observe that there is a weight counterweight at the spindle? No. We have used spring control mechanism. Correct. This is why I asked for. Now, don't you think this is similar to the permanent magnet DC motor? The structure is similar to the permanent magnet DC motor, which is used for the to limit the rotation of this motor. Don't you think so? Yes. So this works whenever the current carrying conductor is placed in magnetic field. So this current carrying conductor is placed in magnetic field. This is these are my magnet and an S pole. This is the circular one. The intersection across we are look. I'm showing you because of just understanding. So the when a current conductor varying placed in this magnetic field, it will experience a mechanical force. Correct. We know this as per the Lorentz law. Okay, as per the Lorentz law. So for the equation, deflecting torque, what will obtain, that is BINA. That is nothing but BINA. Okay, so accordingly, the spring control is used to produce the controlling torque. So spring are made up of which one? The springs are made up of which one? Bronze material. Okay, so here radial magnetic field concept that we have used. Which one? This is noted point, that radial magnetic field concept we have used here. When there is an produce controlling torque, springs are made up of bronze. So because of this, it produces controlling torque. Okay, in ammeter, moving coil is wound on the aluminum former, and aluminum former produces deflecting torque. So aluminum former is producing certain deflecting torque, and this torque produced by deflecting that we have noted out as BINA Newton meter. Okay, so what we are looking for? We are looking for the PMMC, that is torque produced in PMMC is BINA, and the controlling torque is nothing but what? It controlling torque is proportional to the angle of deflection, that is from this position to the disposition. So whatever the angle of deflection, that is nothing but controlling torque. So TC is directly proportional to the theta. Okay, so at as of what we know, at steady state, when this like at this position, at this position, as we have discussed, your controlling torque and the damping deflecting torque are at rest. So TC is equal to TD. Okay, TC is equal to TD. Don't confuse that deflecting torque becomes equal to controlling torque. No, this never happen. Your controlling torque is get produced to oppose the deflecting torque. correct? So TC is equal to TD. Okay, and we know the deflecting torque, that what we get through this electromagnetism, the effect, that is BINA, and from the controlling torque we get a deflection of theta, correct? So Kc is the controlling constant. So we'll write the equation for theta. If we just summarize this one and we just write the equation for theta, so it's come as BINA. Kc theta is equal to BINA, and we just write the equation for theta, so it is BINA divided by Kc. BINA by Kc. So here only the current is the changing, the rest of the things are considered to be constant, that is B, number of then area, then Kc, these all are constant. So theta is directly proportional to the current, since the PMMC is always a linear one, linear type of instrument, correct? PMMC is always a linear type of instrument, and it works on the DC supply. It works on the DC supply. Correct? Now let us solve one numerical based on this. The question is a single phase, single phase 230 volt 50 hertz supply is given to a 0 to 300 volt moving coil instrument, then it reads 0 volt. If you have given single phase supply, if you have given the single phase supply of 230 volt and 50 hertz, so they are saying they will read a 0 volt. Why? Because we are what we have seen so far. We have seen it works. Your moving coil instrument work on the DC source. As what source we are using here? Single phase source. So this is not a DC. It's a AC one. So definitely, your supply will not accept that particular thing. But what's the technical scenario here? Because of this frequency, just let's see. The frequencies of what? As what we are saying, it is only work for the DC, and what we have supplied, you have supplied 230 volt 50 hertz AC. So definitely at this instant we will reject that one, and we will say because of the frequency your pointer, what the AC waveform it considers is a pointer positive half cycle, then for the rest of the thing a negative half cycle. What we required, your pointer should be reflect from the zero to achieve to the final one, correct? So because of this pointer, what will happen, what will happen for the positive half cycle, it will deflect one, for the negative half cycle it will again come back to the zero, and this forward and reverse process goes on, but it never reach to the final position, correct? So this has the limitation of PMMC, that we have always it use with the DC supply only, correct? Yes. Now let's move next. What they have given. Yes. Now next topic is extension range of PMMC. Okay, when we are measuring the high values of DC current through the PMMC, where it is, yeah. So this is the PMMC, or certain we are saying it's a D'Arsonval principle or instrument we have apply here, and we are using on the basis of Lorentz law. We are applying our Fleming's left hand rule, and we are calculating the direction of current also. Okay, so we got the equation, we equate this. Only the condition is TC is equal to TD. We cannot say TD is equal to TC. Okay, it's look like both are the equal, but it's not the case. Whatever, why? Because just now we have seen, as we have started with the deflecting torque, controlling torque, and damping torque, so we have looked for what is the role of TC, what is the role of TD. Am I right? Yes. Then we will move for extension of this PMMC. Okay, Now the question arises, why there is need of extension? Extension means what? Okay, first let me know what is mean by range. Then we'll talk about the extension of range. What do you mean by range? Yes, who is present? What do you mean by range? Range is nothing but range, or we can say minimum or boundary value of minimum and maximum. That is nothing but range. Correct. So at the start of the session, we have discussed about the range. Yes. So when your instrument is utilizing for minimum and maximum range, and it is not acceptable, or it is not get best fitted for your particular application, then what you suggest? You suggest for some kind of modification, because some sort of range we cannot rechange, or we cannot replace the instrument. Like, where suppose example is, we want to measure it for the 100 numbers, and the demand is for 121. Okay, so does it being a business aspect that we need to replace the instrument? Obviously not. So what we look for, we'll try to make some modification in the particular instrument, so that 100 limitation can be extended to 125. So can 120 is can be easily acceptable. Okay, because the range expansion is applicable to the nearby range. Okay, if there's too much change of request, then we'll move for the next experiment, next instrument, or total change of your instrument. But when we require certain small circuit modification in the instrument, then we look for the range extension. Correct. So what they are saying, measuring the high values of DC current by a small circuit modification in the existing instrument is called the extension range of a instrument. Correct. Extension range of a instrument. So let's see what do you, in which way we can extend the range, and we'll solve some numerical. So this is the one which is always been asked in your exam, or GATE exam, 1 or 2 marks regarding range extension. Correct. Yes. So what they are saying for the range extension for DC emitter. DC emitter, what they are saying for DC emitter, look like, first look at the structure, then we'll move for the actual one. What they are saying, in DC emitter, the current is I. This is shunt current. This is shunt resistance. This is total ammeter meter, and this is multiplication of Rm. Now, if we just write the equation for RISH, so ISH means this is a leaving current, this is the incoming current, and this is Im. So what we apply? We apply the Kirchhoff's current law. So we write the equation I is equal to Im plus ISH, and ISH then it will come as I minus Im. Okay. Now this current is flowing through RSH resistance. This current is now flowing through RSH resistance. So which law we will apply here? Yes. Which law we will apply? As we are discussing network. First, let me know. We will apply law or theorem in single diagram. For the single diagram, we will applicable for two laws. Let me know which one. Two simple law we have applied. Yes, algebraic sum of the current flowing through the node or junction is always zero. Which law it is? Kirchhoff's current law. So where we started with the equation I is equal to ISH plus IM. Correct? Don't you think so? Then Then now we'll apply the current law, sorry, Ohm's law. Where current is flowing through the resistance, definitely we will apply Ohm's law. So what's Ohm's law saying? As per Ohm's law, we'll oppose the flow in opposition to the flow of current. So now the RSH is the resistance, current ISH is flowing through it, so it will oppose. Correct? Yes. So we will simply put Ohm's law, that is IM for ISH, IM RM is equal to ISH RSH. Both are in parallel one. Correct? As from this, we will write the equation for RSH. So RSH is nothing but RM upon M minus 1. So here M is nothing but your I minus I, which is known as multiplication factor. Correct? So to the increase, how now the question is how to increase the range. So increase the range of ammeter, a low value of a resistance must be connected in parallel with the meter. So this is very highlighting point. Resistance must be connected in a parallel, but which type of resistance? Low value. Correct? So low value of resistance must be connected in parallel, so it is called as shunt resistance, that is RSH. Correct? Now we will use this internal resistance Rm of ammeter, ideally 0 ohm. Correct? Yes. So this is nothing but range extension of a PMMC for DC ammeter. Now let us solve one example based on that. As they are saying, you can look in the example 2. What they are saying, a 0 to 1 milliampere, a 0 to 1 milliampere ammeter has its internal resistance of what? Internal resistance of 4 ohm. Okay, they have given the internal resistance of 4 ohm, and they are want to extend it the range of 100 ampere. Then the value of shunt resistance is required should be what? They want to extend it up to 100 ampere. Then the value of shunt resistance required is should be what they have given? I, the total current I, that is 100 ampere. This is what they are want to extend, so that total current I should be 100. Im, they are given it is 1 milliampere, and if we put this value, so we'll get the value of m mean nothing but multiplication factor. So m is equal to I upon Im is equal to 100 kilo ohm. So RSH, we have the equation RSH, that is Rm upon m minus 1. Okay, Rm is they have given 4 ohm upon m minus 1, 100k minus 1. So m value how we calculated? 100 m minus 1 is equal to 40 micro ohm. So this is what the equation value for RSH. Correct? Shunt resistance. This is value for shunt resistance. Now, what's what's the value for this ammeter extension? So if what we have used the ammeter extension range for the internal resistance of 4 ohm. Now this range we have extended up to the 100 ampere, and what we are obtaining? We are obtaining for the shunt resistance, that what we required. Correct? Yes. So put these values in this equation, you will get the value as 14 micro ohm. So 40 micro ohm. Correct? That is RSH. We look for another example, a theoretical example. If an analog PMMC, what we are look for? PMMC. PMMC stands for permanent magnet moving coil instrument. Correct? Now this PMMC, if we are using ammeter, is provided with no controlling mechanism, and the moving part are free to rotate. So the reading of the instrument, if the current is 1 ampere DC pass through the moving coil, so the pointer will remain stationary, pointer will continuously rotate 1 ampere or 2 ampere. So the question is, if 1 ampere DC pass through the moving coil, then what will the scenario? Pointer will remain stationary or pointer will continuously rotate. The scenario is it is free to rotate. It is acceptable to the free to rotate use. This is the one. Then tell me the pointer will continuously rotate, it will remain stationary. And the what we are passing? We are passing DC. In previous example, we will look for the source was EC1. Yes. What you are expecting? What you are expecting? Okay, then we will move for the registration by voltmeter. Okay, see, as there is no control mechanism, is there? Have they said there is a what they are saying? No control mechanism, correct? So no control mechanism means your controlling torque will not develop. If controlling torque will not develop, so developing torque will develop because coil is having carrying current. So definitely the pointer will continuously rotate. Why? Because no controlling torque. Controlling torque is nothing but what? TC is equal to TD. It is a equal and opposite direction where force apply torque apply on your deflecting torque. But here the case scenario is no controlling torque is present. So definitely instead of remain stationary, it will definitely deflect. It will definitely deflect, but it will continuously rotate. Correct? Yes. Now let us move further. Right now, what extension we have covered? Range extension of PMMC ammeter. Now voltmeter extension range. Okay. In voltmeter extension range, what they are given? Hmm. Not they are given? Yes. Is anyone who is present over here? Okay. So the volt extension is what? We are having a voltmeter range scenario like this one. See, this is a voltmeter. This is the REM resistance. This is VM. This is RC, that is series multiplier. Now IM is equal to IFC, that is what we are designing. So for the volt extension, we are having VM is equal to V into RM upon RSC into RM. Sorry, plus RM. So M is equal to V by VM, which is nothing but multiplying factor, same as like this one. Here the multiplier fraction is what? I divided by Im. That is the multiplication factor. For the voltage meter, this is V by Vm is the multiplication factor. So that is a full scale. That is full scale voltage. So V is a full scale voltage. Vm is the measure value of voltage. That is M is equal to V by Vm. Full scale voltage divided by measure value voltage. So whatever the voltmeter sensitivity, will calculate it by inverse of your current, full scale current. Okay, so your full scale current is what they are given in terms of RSC plus RM upon V, correct? So yeah, this is one more additive information that our human body resistance is about 600 to 1 kilo ohm. 600 to 1 kilo ohm, correct? Yes. Yes, for our body, human body resistance, it is a 600 to 100,000 ohm. Okay, so based on that, we'll solve one numerical. Let us check a multi voltmeter or the multi range voltmeter. So far, what we have look for, we have look for only the single voltage. Now there are multi-range voltmeter is there. Shown in figure, what there is a full scale deflection of 50 microampere and meter resistance of 1 kilo ohm. Full scale deflection of 50 microampere and meter resistance of 1 kilo ohm. What are the values of resistance R1, R2, R3 respectively? What they are, understand the question very carefully. Multi-range voltmeter is shown in the figure with full scale deflection current. They are saying it is a 50 microampere. Maximum full scale deflection can be possible. It is a 50 microampere, and the meter resistance is 1 kilo ohm. Meter resistance one. What are the values of R1 and R2 and R3 should be? Okay, so let us understand. Okay, they have given the options: 100 kilo ohm, 200 kilo ohm, 1000, 101, 201, 101, 99 kV, 199 kV, kilo ohm, 999 kilo ohm, 5 kilo ohm, 10 kilo ohm, 50 kilo ohm. Okay, so what is the range extension formula? As what we are look for, range extension formula is Rm into V1 upon Vm minus 1. So V is the given, Rm they have already defined, and Vm they have defined. So Rm into V1 upon Vm minus 1. Rm what we have? So 1 kilo ohm resistivity they have seen 1 kilo ohm. So we start with the meter resistance. Meter resistance is 1 kilo ohm. So we'll simply put the value of 1 kilo ohm. Then V1. V1 what? First we will connect at this one. Okay, this is by default connector, so we'll start with this one. And they are also asking for calculate R1, R2, R3 respectively. So anyhow we have to calculate R1. So we'll start with that one. That is R1 is equal to R1 is we need to find out, and for that voltage is nothing but 5 volt. Okay, so we'll simply put the value of V1 as a 5. Now what is voltmeter? Meter voltage. So meter voltage they have given as 50 micro into, they have given the current and they have given the resistance. So definitely we will just V is equal to IR 50 micro into 1 kilo minus 1. So if you just simply put this value, if you simply put this value in the equation, so you will get the values. So just put this value and let me know whether you obtain the same value or not. Okay, just check it. Only you have to change the voltage source. Correct? That is, first you have to take 5 volt, then you have to take 10 volt, then you have to take 50 volt. Okay, just simply put this value in equation and let me know what you obtained. Yes, have you obtained the same values? Yes, have you obtained the same values? Don't believe on this one. Okay, you have to try it by yourself. You have to try it by yourself and let me know you obtained this value. Okay, and just check. Yes, here in option C we have the same values: 99 kilo, 199, and triple 99. Okay, yes. Then we will look for one more numerical. Let me know where it is. Yes. First, we'll understand the tips that what we have learned for today's session to solve voltmeter with different reading. Okay. So if the voltmeter reading is given in V and SV, so we can use RS plus RM is equal to SV into V, RS plus RM upon V is equal to SV. If the ammeter reading are given in R and the full scale the current deflection is RFS, in that case RS plus RM is equal to R. If V and IFS, that is full scale deflection current and voltage are given, then R plus RM is equal to V upon IFS. So RES is nothing but series resistance multiplier, multiplier resistance, and REM is nothing but your meter resistance. Got it? Yeah. Now, yes, IFS is a full scale deflection. So what you obtain from our relation, the final individual meter resistance R will get from this equation. Okay, so try to just note down this one. These are the most important tips as a gate point of view. That okay. Now we'll move further. Okay, moving on, we'll look in next session. Let me just show you what. Yeah, the one more example we'll look for. See, what the question. Read out the question and let me know the answer. I'll hide answer. Yeah. Let me read out the question and let me know the answer. So what they are given in the circuit shown in the figure, voltage across R2. Where is R2? Where is R2? R2, R2. Yes, R2. Voltage across R2. Yeah. So that is this one. Is measured by two different voltmeter P and Q. Voltage across R2 is measured by two different voltmeter P and Q, having sensitivity of 1 kilo ohm per volt and 20 kilo ohm per volt. Correct? Having sensitivity of now I think you know the difference relation between the sensitivity and this. Okay, so you can mark out this one. SV is nothing but your voltmeter sensitivity. So if you are confused with this, these are nothing but your sensitivity. Correct? Voltmeter sensitivity. Okay, so this equation is for voltmeter sensitivity. Voltmeter it is giving V and this SV is nothing but voltmeter sensitivity. In that case, what will be your equation? So in that case, Rm is the meter resistance, Rs that what we are need to connect in series because it's a voltmeter reading and is equal to SV into V, that is voltage voltmeter sensitivity into voltmeter reading. Correct? Yeah. Now where we are, yes. Then they are saying if voltage across R2 is V, okay, fine. Measured by two different voltmeter P and Q, okay, having sensitivity 1 kilo ohm per volt and 20 kilo volt. Both the meter are used on 50 volt scale. Which of the following statement is true? So statement they are saying where it is? Yeah, here it is. So statement they are saying okay, statement are itself an option. So we have to select the best one. Voltmeter P will read more accurate than voltmeter Q. Voltmeter P will reading. So voltmeter P's sensitivity is what? 1 kilo ohm per volt. Okay. So voltmeter P will read more accurate than voltmeter Q, as they are saying. In second case, they are saying both voltmeter read same voltage. Both voltmeter read same voltage. That is 1 kilo ohm volt per meter and 20 kilo ohm per. No, that will not possible. Let us move for the third option, that is voltmeter Q will read more accurate than voltmeter P. Okay, so voltmeter P is having a sensitivity of, okay, 1 kilo ohm, and the Q is having sensitivity of 20 kilo ohm. Okay, now let us understood the equation where it was the relation. Yes, what they are saying, voltmeter sensitivity is nothing but SV is equal to 1 upon 1 upon fc, that is nothing but ohm. So those who are having high sensitivity, those voltmeter who are having highest kind of sensitivity, that will be the highest preference one. Okay, so in this example, which one is having high sensitivity? 20 kilo ohm resistance, correct? So that is nothing but your Q. So options should be yes, answer is C. It means that voltmeter Q will read more accurate than voltmeter P. Both are useful for the measurement, but comparison to that, the sensitivity is more for that one, that is nothing but Q. So we'll include Q for the measurement, correct? Yes. Yes, here the solution also they are saying voltmeter will have with higher sensitivity will give the more accurate result. This is what they are saying. So the voltmeter Q, that is 20 kilo ohm per volt, is having a kind of high sensitivity, so that it will measure the high one, and the voltmeter P is of having sensitivity 1 kilo ohm per volt, so it is having less compared to that one. They are not asking for the to try to solve the example. Such type of questions also ask in GATE exam. They give all this thing, but just ask for the based on the logic. What's your logic says? Okay, such type of questions are asked. Okay, then we have the moving iron instrument. So as for now, what let us just recap what we are look for. We have look for, we have started with the types of indicating instrument, the electrical instrument, that is absolute one, secondary one. So among that, we have classified this secondary instrument as indicating, recording, and integrating instrument. Correct? Indicating, recording, and integrating instrument. Okay. On the basis of that, so indicating instrument is was what? Your PMMC, MI, dynamometer, wattmeter, frequency meter, power factor meter. These are your indicating instrument. Compared to the recording instrument, we are having your wattmeter, oscilloscope. You might have come across this one, that is recording voltmeter, recording wattmeter, record storing oscilloscope. And the third one that we have looked for the indicating instrument, that is energy meter, kilowatt hour, and the ampere hour meter. Okay, apart from that we have looked for different torques, that is deflecting torque, controlling torque, and the damping torque. Okay, so we have looked for three types of torque: deflecting, damping, and controlling. Okay, we have looked for the each every one functionality of each and every one, and according to that we have looked for certain effects: magnetic effect and the electrostatic effect. So we have summarized two instrument, that is PMMC, and also we have solved some numerical based on this spring control and gravity control. Then we look for the friction damping scenario, that is eddy current damping. Then we have a rear friction damping, and we have fluid friction damping. Okay, this is the keyword that we have looked for: effectiveness order, that is eddy current is always more effective than fluid friction, and it is always more effective than air friction, correct? Yes. Apart from that apart from that we look for the construction, not exactly construction, we have looked for the technical specification and its working of PMMC, that is permanent magnet moving coil, which is nothing but We check for the TC and TD and we solve some numerical. Correct. Then the most important part of extension range of PMMC. So here we have utilized DC ammeter voltmeter range, then we have solved some numerical based on that, and then we look for the voltmeter series multiplier, that is voltmeter range. Correct. Yes. Now, okay, we are enough to close this session for today, and we'll continue in next session. Okay. Yes. So in next session we'll come across moving iron instrument. Then we'll divide it by attraction and repulsion type instrument, and accordingly we'll move for solving some numerical. Based on that, we'll move further. Okay. So we'll skip this part. So this kind of part, derivation and all, we'll directly look for the gate perspective. Yes. Okay. So till now, if you have any doubt, you can ask. If you have any kind of doubt, you can ask. Then we'll close this session. Yes, till the time you can record, note down this one. These are the mostly important, frequently asked for to so one only one formula equation. Yes, till the time other students can ask for the if you have any kind of doubt. Okay, I hope you have noted this one. Okay, tomorrow we'll continue with this moving and MI instrument. Okay. Yeah. Okay, so now just 1 second.